So by now you've probably seen a few of the Khan Academy videos about logarithms, and you're all firm in your laws of logarithms and you're totally under control of the whole thing. But you may have noticed that the base of logarithms tends to disappear. We're used to, in all of the laws of logarithms videos, you see things like log base b of a is equal to whatever. But when you see it in textbooks or in assignments, or when, say, Tulda's giving a lecture next term, it's just going to look like the log of a is equal to x. We assume everybody already knows what base we're using, and that can be a little bit complicated because different people assume different bases. So the bases that show up most often, the most popular ones, are log base 2, log base 10, and log base e. Log base 2, well, let's give it there. So log base 2 of x, log base e of x, and well. So log base 2 is called a binary logarithm. It shows up a lot in computer science because computer science has a lot of binary counting systems. Log 10x is the one that shows up most frequently, so frequently that it's called the common logarithm, and it makes a lot of intuitive sense to people because all of our counting systems are base 10. And when you're watching Khan Academy videos, Sal means base 10 when he's talking about logs. But in population dynamics class, we're going to use log e of x, which is the so-called natural logarithm. And you probably know by now that e is a constant that's approximately 2.7182818 goes on forever. Also, sometimes people refer to it as ln of x, but we're not going to do that. So whenever I say log x, the e is implied. So that means this, as far as you're concerned in this class. So why is base e so special that we're going to refer to all logs as base e logs, or only use base e logs, I should say, unless otherwise specified? So in order to explain that, I'm going to show you the special role e has to play in population dynamics, which is its part in the equations for exponential population growth. If you've seen this derivation before, you can skip the rest of this video because you know why we use log base e. So let's say we start off with some population of organisms at time 0, so n at time 0, we'll call it n naught. Time moves forward in discrete intervals. Time is going to go from 0, 1, whatever, up to big T, which is kind of irrelevant. And we're going to define another quantity, which is r, which is the growth rate of our population, by which I mean the number of individuals at time t plus 1. We're going to define that to be equal to the number of individuals at the previous time, plus some proportionate increase. So the growth rate times the number of individuals that there were before. So then we can rearrange this a little bit, and we say n at t plus 1 minus n at t is equal to r at t, which basically means that the change in n for any given change in time is equal to r times n at time t. Another way to write this is to say that dn, which is just another notation for the change in n, divided by dt is equal to r n of t. Rearrange that one more time, we get dn over n t is equal to r dt, and I'll run out of space, which is okay because the next step here is to integrate both sides of the equation. Dn over n t is equal to the integral of r dt, which means I need to take a little bit of an aside and talk about integration and what it means. About e. We all have this vague understanding that e is equal to 2.718 blah 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 that goes on forever. And the definition of e, or one of them anyway, is that the log base e of any number, we'll call it a, is equal to the integral between 1 and a of the function 1 over x. So we haven't talked about integration yet. Another way of thinking of this that is officially mathematically true is that the integral from 1 to a of the function 1 over x is actually equal to the area under the curve 1 over x in between 1 and a, this area. That's what that means. And the definition of e is the only number that makes this expression true. An interesting sort of corollary of this is that the log base e of e is equal to 1, since the log base anything of itself is 1. That means that the area under the curve 1 over x between 1 and e is equal to 1, which is one of the other definitions of e. But the important thing for us is that since log base e of x is the solution to the integral of 1 over x, that means in our earlier derivation, when I wanted to know what the integral of this was, it's going to be log base e of n. Okay, so let's go back to our original derivation, wherein the original point is to find out how we can predict the value for n at any time t given n at time 0. Which I think I may have actually skimmed over that at the beginning. Anyway, so we're at the point of knowing that the change in n divided by n is equal to growth rate times the change in time. And then we were going to integrate both these guys, basically to get rid of the dn and the dt. And we know now that this is going to be log base e of n at t. And this, because of some calculus stuff you should maybe take my word for now, is going to give us r times t plus something called a constant of integration. Since we want to know n at t with respect to n at time 0, let's say if we set time is equal to 0, then this is going to cancel out, and you get log base e of n at t is equal to c, and since where t is 0, that means log base e of n0 is c. We run out of space up here. So now our original equation becomes the log base e of n at t is equal to r times t plus the log base e of n at time 0. Now we can rearrange this to be the log of n at t minus the log of n at time 0 is equal to rt. Using our laws of logarithms, we know that this is the same as the log of nt divided by n0, which is still equal to rt. To get rid of the log, we exponentiate everything, so we just get back nt divided by n0 is e to the rt. Rearranging one last time, finally we get the official equation for exponential growth. N at time t is the n at time 0 times e raised to the growth rate and the number of time steps. And since this equation shows up everywhere, it makes a little bit more sense now why, in this class, logs without a specified base are always, always, always log base e.